Well, good morning, everyone. It's nice to be able to come to Potsdam after a couple of decades and be part of this conference. And one of the things I really wanted to talk about was the constraining geotherms and through other parameters, and then what thermal parameters one gets from it out of that out of those constraints, and then what do they mean and how I could use them and so on and so forth. But after yesterday's discussions about proxy parameters, I thought that I need to give you folks a primer on Curie depth analysis as well as we go along with this. Well, but of course, I don't want to deviate too much, so I have added only a couple of more slides to my intended talk. And then I still hope that in the end you would be able to give me some ideas about how to use these sorts of analysis and methods. So constraining, this is sort of a schematic diagram through the lithosphere, if you will. And you can have constraints on geotherms through a lot of different sources, surface heat flow, perhaps a Curie temperature. And these dashed lines at about 580 degrees centigrade is meant to be the Curie depth of magnetite. Curie depths of different magnetic minerals are different. And so you have to be a little bit careful when you assume magnetite all over the place all the time. This other pink line or magenta line is solidus, just to give you an idea of where things may be in terms of solidus and how and when the geotherm may intersect the lithosphere asthenosphere boundary. And so there are constraints that one can obtain from S-wave velocities from here. There are constraints on temperatures one can have from seismic velocities at the moho, and so on and so forth. And then there are, of course, lots of other petrologic constraints and thermobarometric, geothermometric constraints, and so on and so forth. But one of the things that these constraints do for us is that they provide additional information. And say, in some sense, the indirect constraints are you get are, say, for example, radiogenic heat production ranges, thermal conductivity at different depths. One can also having constrained the mantle part of the heat flow, temperature gradient variations in the mantle, melting, estimates of melting, or at least conjectures of melting, and then mantle dynamics. So a few years ago, my colleagues Paul Morgan, Tony Lowry, and I did some analysis and figured out that if you take the solution of steady-state heat flow equation and with your customary boundary value conditions, and if you add a constraint of temperature at certain depth, and I'm using Curie depth as an example, then a lot of things fall out of this, and in the end you get an estimate of radiogenic heat production, or ratio of radiogenic heat production and to thermal conductivity. And and this is a bulk value for the crust, if you will, or up to the point where you have constrained the temperatures. Now, I want to be able to use that, but before I do go on to that, I do want to talk about some of the advances in determining the base of magnetizations. And yesterday you saw a number of papers related to that as well. And in determining the base of magnetization, one generally looks for the spectral analysis and annularly averaged spectra. And those spectra sort of look like this. There's a log of power versus wave number. And if you are sensing the base of magnetization, then there is a peak in the wave number that in the spectra that you see, and that the location of the peak is related to the depth of base of magnetization. Now, this is one of the most difficult problems in magnetics, and that is because it involves long wavelengths in the magnetic data, and in most places in the world, most of the aeromagnetic surveys, marine magnetic surveys are done over very short areas, and they don't have long wavelength information. And which means you have to compile a lot of different surveys together. And if you mess up compiling those surveys, which often happens, then your long wavelengths are already corrupted. With a corrupted long wavelength data, you have no chance of getting anything right, unless if it is just serendipitous. The other part of the spectrum over here, the slope, is leading to the top of the magnetic layer. So these are the two fundamental issues over here. And there are a lot of papers and a lot of people who have worked on this from 1970s on to 1995. Then there are more advances and more advances. In the middle over here, there is Akiko Tanaka in one of these dots sitting out there too with an important contribution, and so on. So in the 1990s, it was recognized that the magnetization in the Earth's crust is actually fractal. And that fractal magnetization leads to getting rid of that peak in the magnetization that I was just talking about. I'm not getting a hang of this. A peak in the spectra. So the peak is no longer present, and then as a result, the estimates in magnetization, estimates to the base of magnetization are always deeper. So if you are able to correct for the fractal magnetization, then your estimates change. And so one of the methods that we developed in the last decade is called the de-fractal method, which successively tries to remove the fractal behavior of the magnetic field and determines both the fractal parameter of the magnetic field and the correct depth to the base of ferromagnetic layers. And that was developed by one of my colleagues, Ahmed Saleem, and I, and some of the other folks working with us. So the base of magnetic layer, another aspect of this, that yes, it can be Curie temperature. It may be related to magnetic mineralogy. There have been a lot of ideas since 1970s that MOHO could be a magnetic boundary because of the mineralogical considerations and so on. But there are other magnetic minerals also, like titanomagnetites have lower Curie temperatures, hematite has a higher Curie temperatures. Depending upon where you are, things change a lot. There are also some of the other limitations that are involved, and one of the things is that you need large areal sizes in order to obtain Curie depth estimates, and especially for the de-fractal method itself. And these estimates tend to be extremely tedious to compute. It takes me, by the time I check out all the possibilities on the spectra, it takes me about a day and a half to get one estimate. And then I have to cross-check it with a lot of other things. And so it is actually a tedious process. So I do not, there are newer ways of doing this using wavelet analysis like showed yesterday. But I generally do not tend towards automatic Curie depth estimates. I was going to tell you something about the window size effect on the depth to the base of magnetization. And there are different spectra from the same region, I think in Australia. I don't remember exactly which region we were using for this as an example. but the window sizes were different window sizes over the same region were selected in this. And so this is a spectra from 100 kilometer by 100 kilometer, 300 kilometer by 300. This bottom is 1,000 kilometers. And remember, you are getting your depth estimates from the slopes of the spectra. And the slope over here is much, much shallower. And so you get a shallow depth estimate. For the same region where the base of magnetization could be quite deeper. And so as you go on, increasing your window size, your estimates in this region are getting steeper and steeper and steeper. And you can see that these three slopes almost look very similar to one another, but you can see the estimates coming from them are like 50 kilometers, 65 kilometers, 75 kilometers. So there is a lot of error that is involved because of accurately figuring out the slopes of these spectra. And so these are some of the aspects that are really, really important. So I told you that you need to have accurate long wavelengths in the data, and we managed to do that in early 2000s and published a database that was related to the North America and primarily related to the U.S., where we were able to use continuous geomagnetic main field models and ionospheric models and so on in order to correct for North American magnetic field data sets. And so this data can be actually used for base of magnetization estimates. So these are the base of magnetization estimates in the US from that corrected data. And you can see that the western US, you have shallower base of magnetization, as one might expect. Now remember, these are coming from fairly large window sizes. So with these fairly large window sizes, you cannot detect very narrow regions of changes in Curie depth and so on. But nonetheless, we have a better general idea of the picture. There are a lot of lines over here, and so these are sort of like the geochronological provinces in North America. In the West, in addition to those, there are some physiographic provinces plotted over here. And so this is the region of basin and range. That's where you expect lower Curie temperatures, lower Curie depth, and that is where we are getting those. Many of these regions are actually quite consistent. Many of these estimates are quite consistent with what we know. Some of them are not. We need to look further into those details. For example, in this region of Paleoproterozoic, we get shallower depth of magnetization. And these are really solid estimates. I've spent a lot of time doing this. I've analyzed every possible source of error, at least coming from the spectral estimates. And these are shallower estimates than what one expects in these regions, and that is where I think is related to titanomagnetite as a Curie, as the magnetic mineral which has a lower Curie temperature. But let me move on to some of the other things. These maps that we see of the Curie depth estimates are actually fairly consistent in many parts with respect to the surface heat flow map that we have a fairly good database over the US. You do have a lot of active tectonics and high temperatures, high heat flow in the western US. And then there are pockets of here and there that are relatively higher compared to the background values and so on. But more or less things are consistent, except when the magnetic mineralogy may be different. So with this Curie depth constraints, we can actually tease out what could be a very important. Okay, sure. I have no problem, but I'll just cut out some of my talk because I had to add some other things in order to explain to you where these Curie depths are coming from and so on. So we can tease out this ratio, as I showed you through the equations on the second, third slide. And so we can also use that in a more creative manner. So you can vary the thermal conductivity. Then you can, of course, using that ratio, obtain the bulk crustal heat flow. And then for that, each combination of radiogenic heat flow and thermal conductivity, that requires a certain amount of basal heat flow, or the reduced heat flow, if you will, to match the surface heat flow that we are trying to match. And if you know what your reasonable reduced heat flow should be for the region or the range of it, then you can get estimates of bulk radiogenic heat production and thermal conductivity in order to compute geotherms. And here there are a number of geotherms I've plotted over there, but they are just to show the range of reasonable values that we get out of the technique like this. And then this black one is what you had no information and used just standard parameters. In this particular case, you would end up with much cooler geotherm in that particular case. Now, as you see over here, the radiogenic heat production is fairly high in some of these ones, but these happen to be coming from granitic, highly radioactive granitic regions in New Hampshire. And so in this particular case, the Curie temperature-constrained geotherms in New Hampshire, at least, are consistent with the high radiogenic heat production rate values that you have. And also, that means you have higher crystals temperatures than if you had no data and you were just trying to use standard parameters and so on. So since I have run out of time, I'm not going to go on with the rest of my presentation, but I'll let you ask me questions, and maybe you will have any thoughts about how I could use this better and try to tease more out of it, even not right now, but maybe later in the day and so on, maybe by email communications. I'll be very happy to know that. Thank you.